everyone. We're going to do problem 48. If you were watching the last video, we already started on problem 48. And so you can run and get ahead if you like. We had said that we were going to do a U-Substitution. We let our U equal 1 plus 2x. You notice I went and got a different pencil. And our du was equal to 2dx. And so I like to put a box around that. And then we get here du over 2 equals dx. And training wheels on my algebra here. And then we made a plan for our bounds as well. We said that for our low bound, which was x equals 0, that u equaled 1 plus 2 times 0, right? Because this is what it equals, so that was 1. And for our upper bound, x was equal to 4, and so u equaled 1 plus 2 times 4, which is 9. So we had plugged all this in. So this is, instead of 0, we were going to put 1 for u, because we're turning everything into u's. And for instead of 4 for x, we're going to put 9 for u. We're turning everything into u's. There wasn't something to get rid of that x, and we have the square root. 1 plus 2x was u, and then this is du divided by 2. And if you like, you could put that half out in the front. This 2 here is a half, and I'm going to do that this time just because I already know that some of my friends were going to be kind of bothered by my next thing that I had. I already have some people that have let me know. And so remember what we said that we were going to do about x? Do you guys remember? We went over here and we took this equation u equals 1 plus 2x, and we solved for x. U minus 1 equals 2x. U minus 1 over 2 equals x. And I'm going to substitute in for x u minus 1 over 2. Or 1/2 u minus 1 equals x, right? That's another way of putting it. So I'm going to write it that way here. And, whoops, my new pencil was so great. U minus 1. So when I do put that here, this half and this half, you could pull that half out to the front and becomes 1/4. Half times half is 1/4. So that's where we were in the last video. And I asked you guys, hey, do you think you can go and solve it? And so I still have a division, but what I need to do is I need to divide those. Now it's something I can divide. It's a binomial divided by a monomial. And so the beginning of the problem wasn't something, here I go, here, wasn't something I could divide. I couldn't divide that, you know, and so now I can do the division. So this is 1/4, the integral 1 to 9. I haven't taken the integral yet. So this is going to be u to the first and then divided by u to the half. So 1 divided by 1 minus half is u to the half. Minus, and then 1 over, this is going to be negative, right? U to the negative half, du. And now I can totally find the integral. So the integral here is you add 1, u to the 3/2, and you divide by the same darn thing. But dividing by 3/2 is the same as multiplying by 2/3, right? So I'm going to multiply by 2/3 instead. And I still have the 1/4 hanging out here, lurking out there. Minus, and then I'm going to add 1. So when I add 1 here, I get u to the half. And I'm going to divide by the same darn thing. And dividing by a half is the same as multiplying by 2. And I don't need plus c, right, because I have bounds here. And though these are u's, 1 and 9 are u's. So I'm going to plug into u. A lot of times people will go back and they'll change it to 0 and 4, and they'll plug those in. But 0 is a value that goes with x. So you wouldn't want to plug it into u. So I'm just going to keep with this. So this is going to be 1/4. And then I'm going to have my upper bound minus my lower bound. So this is, and then the whole thing times 1/4, right? So it's easy to lose your algebra here, lose your arithmetic even. So 2/3 times 9 to the 3/2 minus 2 times 9 to the 1/2. That's the square root of 9, by the way. And then here, 2/3, 1 to the 3/2 minus 2 times 1 to the 1/2. And then, and so this, and the whole thing here is multiplied by 1/4. So I'm going to figure out what this is, what that is, subtract them and multiply by 1/4. You can probably put it in your calculator if you're fairly tricky, just like you see it, and it should be all fine. And so however you want to go is great by me. And so this is the part that more people make a mistake on than the calculus part, believe it or not. And if I'm going to make a mistake, it's right here. So I'm telling you that, and you probably know that I'm going to make a mistake here. And because that's just, when I start advertising that a mistake is going to be made, it seems like it's not too long before I make a mistake. So here we're going to have this part right here. I just did that, was 12 minus. Now I'm going to go do that part right there. Now I think I probably should be able to do that part in my head. And I probably could have done the other one in my head too, but I was trusting my head because my head hasn't been drinking any soda, and so my head's not clear. And so 12 plus 4/3. So I get 1/4 of 40/3. And so when the dust clears, this is 10/3. Okay, so we did a lovely, 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 lovely job on that problem 48. And I had to do it in bits. I ran out of room. I kind of learned, I can't do no editing on these videos. I might at some point learn how to do editing. My son says that he's going to show me how to do editing. And I think to myself, you know, YouTube stars, they get all kinds of likes and all of that. You know, they put out 1 or 2 videos a week, and I'm putting out like 4 videos a day. And so there can be no editing. And so I just have to hope I don't say anything too obnoxious. Okay, and so this is evaluate the indefinite integral. And they might also say find the indefinite integral, and I'm not sure. You know, I might have typed this from a previous book, and I'm not sure if our book makes a real big deal on whether or not it's evaluate or find, and it doesn't matter to me that much. So I don't have bounds, so I know that I'm going to have plus C when the dust clears here. And I'm thinking to myself, well, if I've memorized, so 2 ways of going, right? And so this is the memory way. I've memorized that the integral of secant squared ax dx equals tangent ax over a. Okay, so if you've memorized, and you can find the derivative of this and verify that that's what it is equal to, if you like. And if so, plus c, if you like, put a plus c here. And so I have that memorized. And so if you are a memory person, then that's basically what I have here, right? Secant squared 2 theta, it doesn't matter the variable, d theta, then would equal, I don't know why I put a parenthesis there, would equal tangent of 2 theta over 2 plus c, right? So that's what that would be, and that's just using the memory way of going about it if you have this memorized. So the other way of doing it is that you could say that you have an inside function here, and that inside function is 2 theta. So u equals 2 theta, then du equals 2 d theta, so that du over 2 equals d theta, right? And then this will convert this into secant squared of u, and then du over 2. And then you could put the 2, it's half out in front, so 1/2, and the integral of secant squared u du. And then here you have to have your memory, right? And you have to know, you have to have memorized that the integral of secant squared x dx is equal to tangent of x plus c, if you like, right? And so you can kind of see the two memory verses are really similar to one another. So there's really not a reason maybe not to have this one in your thoughts. But okay, anyway, so when I take the antiderivative here, I get half of tangent of u plus c, because I don't have bounds, and then nobody cares about u, so half of tangent of 2 theta plus c. And you notice that we get, that's exactly the same answer that we got over here. So wrote it over 2 instead of as half, either way, half dozen each to the other, right? So anyway, so either one of those is good with me. I don't care at all. They actually threw a few problems like this in to the previous section before they had shown you this U-substitution. So, but our book didn't show us the memory verses of our trig like this. But the last book we used did, and so I still have that. Of course, you didn't use the last book like me, and so I still have that in my mind, and actually thought that was a good idea to do that, because this seems to come up quite a bit, that you just have a coefficient there. Now, if it's more tricky than just a coefficient, this is all this is a coefficient, then you would have to use the U-substitution. Okay, so here they're asking us to evaluate the indefinite integral, and so I'm looking at that, and I'm thinking, you know, will it be helpful to? It's a division. Could I get using trig on it and convert it around, and that's one way of going. And so there's multiple ways of doing this problem actually. Or would a U-substitution work? And if you're thinking about a U-substitution, then you have to figure out what your inside function is, and you're trying to gobble up with your derivative the other function. And so, you know, I kind of have in my mind that if I take the derivative of tangent, I get secant squared. So if I think of this secant squared here, and if I think of this like this as tangent x dx, then it kind of works out that if I let u be tangent, then my du will have a secant squared in it, and it'll gobble that up. And so you kind of get used to that when you've practiced some, because you're kind of thinking about how would I get rid of the other piece, right? If I let my u be secant, then the derivative of secant is secant times tangent, and that doesn't get rid of my tangent squared down there. And so anyway, and letting your u be your denominator is a really, really helpful thing a lot of times too. If you have multiple places that seem to have an inside function, a lot of times focusing on the denominator, because that makes a monomial in the denominator that you might then later be able to divide by. Anyway, so just another hint. So this is my plan, and I do plan to do this problem more than one way for my friends that like variety. Right? So du equals secant squared x dx, so that du over the secant squared x equals dx. And so this is what my planning on plugging in is going to go. So this is going to be the integral, and I'm going to leave I don't have a substitution for that, but I have a substitution for this, right? And then the dx is du over secant squared x. Now, this is a way of writing it. There's a lot of other people that would have also circled this And it's another way of going. It's the same story, right? And they would have said, oh, secant squared x dx is du. And they would have substituted that whole piece for du, and they would end up with the same thing that I'm going to get right now, right? So it wouldn't be different. And like I said, all of this is good. It's all good. And so this is the integral. Now I can't find the integral when I have it written as 1 over u squared du. I have to write this instead as u to the negative 2. So this is the integral of u to the negative 2 du. And now I can use my power rule. You add 1, so that's u to the negative 1. So when I add 1, and divide by the same darn thing. So that would be what it would be. And what do I need plus c because I didn't have bounds. And so this, oh man, I'm going to write this as 1 over u. Is that okay? Negative 1 over u plus c. And so this is negative 1 over tangent, because that's what u is, tangent x, plus c. And I know that 1 over the tangent is the cotangent, right? So this could also be the negative cotangent plus c. Okay, so there we have done a lovely job on that. And so, but there was another way of going there. And so I want to show you that other way of going if you were interested on it. Folding some paper up so that I have some paper to write on here. And just to try to do the problem again. Now the other way that you could have done the problem is with a trig substitution. So we used a U-substitution and it worked out beautifully. But you could have done a trig substitution. And what I mean by that is that we know that secant is 1 over cosine and tangent is sine over cosine. So that if you would have done a little trig substitution, this would be 1 over the cosine squared for the secant in the numerator, right? And in the denominator, sine squared x over cosine squared x. My integral sign needs to get bigger to go with that complex fraction that I've created, right? And the good news is that they're both divided by cosine squared x. So that would reduce out, that's 1. And so this becomes the integral of 1 over sine squared x dx. Now I don't know how to find the antiderivative of 1 divided by sine squared x dx, but I remember that, hey, sine, 1 over sine is equal to the cosecant, right? So this would be the integral of the cosecant squared x dx. And guys, that's a friend, right? We know what that's equal to. And so it's one of our memory verses that we have. Now, you guys are probably thinking that you don't have to memorize all these things because of the fact that we've gone to unproctored test, and you could kind of cheat and look at it. And if you do that, I probably won't know about it, but your Calc 2 teacher will know about it, and they'll tell me about it. And so right here is the integral of secant squared x dx is equal to negative cotangent x plus c. And so if you want to be a STEM major, you want to know all of these. You want to have them in your head. And so write them on your heart. And you notice that that was the same answer that we got here, right? Same exact answer, negative 1 over the tangent x or negative the cotangent plus c. So we did a lovely, beautiful job on that. And we have another one to do. So I'm on too many examples, as always. But too many examples is not as good as not enough, or I don't know, whatever you want to say. So I have this one to do, and I'm like, oh, well, I can't multiply those together, so I can try my U-substitution. So my plan is to let u equal 2 plus x. And then du equals dx. And no help for getting rid of the x squared out here. So it's okay though, right? So I'm going to have here x squared, the square root of u, and then du. And I lost the square. I said x squared and then didn't write the square. And so, but remember what we did? We came here to our u and we said, let's solve that for x. So that's u minus 2 equals x. And so we're going to be substituting in, right where we have x, u minus 2, quantity squared, times the square root of u du. I got all excited thinking I got a text. My phone's sitting over here. I thought, oh, somebody's texted me. Somebody loves me out there. And it was AT&T telling me that thank you for sending in a payment. And so I guess somebody still does love me, right? Now, this is a binomial times a monomial, and so it might make you feel better to write it as a monomial times a binomial. It definitely does, my algebra students. If you don't care, then you don't have to do that. And then you want to FOIL this out because it's still a product. But it is now a product that I can multiply pretty easily together. So I just FOILed that out, right? And I hope I didn't make a mistake. And then now I'm going to do the distributive property here. And so I turned it into something I couldn't multiply together, can't multiply it together. So I used my U-Substitution into something that I now can multiply together. And so this is going to be my integral of u to the 5 halves, 2 plus half, minus 4u, so this is 1½ is 3 halves, plus 4u to the 1/2 du. And I'm going to have to write this up here when I take my integral because I'm just kind of running out of room. Okay, so when I add 1 to the exponent, so if I add 1, that's 7 halves, so that's u to the 7 halves, and you divide by the same darn thing, which is 2/7. And then minus 4, that holds still, and u to the, and you add 1, so that's 5 halves, because now I can just do the power rule. I call it the unpower rule, of course, because we had the power rule for derivatives, and I want to think of it as the unpower rule, right? And then I'm going to add 1, so that's 3 halves, so this is 4 u to the 3 halves, and you divide by the same darn thing, which is the same as multiplying by 2/3. Since I did not have bounds, I'm going to put plus c, and I'm going to have to make sure that I clean this all up and go back to u, which was 2 plus x, because no one cares about u, right? So this is going to be 2/7, and then instead of u, I'm going to have 2 plus x raised to the 7 halves, minus, and then this is 8/5, and then instead of u, we're going to have 2 plus x raised to the 5 halves, and then plus 8/3, 2 plus x raised to the 3 halves, and then plus c. So there's our lovely answer. You might be thinking, if I took the derivative of that, I don't think I would get back to that. But if you took the derivative of it and you did some tricky factoring, I bet you would get back to that. And so you should definitely give it a try. These ones where you have to do this tricky, you know, after you plugged in, you didn't get rid of all the x's on a natural, so you had to go back and you had to solve this for x and then substitute it in. My son Tyler has named those a double sub because you did the substitution once, but it didn't get rid of all the x's. So you went and you made more of a plan, and then you substitute in it again for the double time of doing the substitution. And so I don't know. It makes me happy because someone I love very much named it that, and so it's his own name for it. And so he was so cute. You should have seen him when he was learning calculus. He'd say, "Oh, it's a double sub," and I'd think, "Yeah, it's a double sub. That's what it is." Okay, you guys are cute when you're learning calculus too. So if you're worried that you're not cute, you are. Okay, one more thing, and then I will be done, definitely done. No, I'm not done forever. These videos are long, man. Tell ya. Okay, so they tell you in your book that if you have an even function, and remember that an even function is symmetric with respect to the x-axis, y-axis, and that it follows that symmetry rule, right? And so if you try to take the integral from negative a to a, so I'm just going to put over here that this is a, negative a, and then over here at the same spot, right, I'm going to try to draw it in the same spot, is a. So this distance here is negative a, and that distance over there is a. And they say that, and you can kind of look at this, that all you would have to do is, so here's that, right? And look what you have over here, a mirror, a mirror, a mirror image. And so they say that instead of going from negative a to a, if you liked, what you could do instead is you could go twice from 0 to a. Now, why that sometimes is helpful to do is that when you do the up bound minus the low bound, since that's the place that people make a mistake on, and a lot of times when you do minus and then you plug in 0 into your function, it's a lot easier. So that's a reason why you might want to do it. Whereas if you plug in negative a, people have the opportunity to make boo-boos, make mistakes with their arithmetic. And since that's the place that most people make their mistake is on that arithmetic, well, making my arithmetic easier might be a good thing. Now, an odd function is even better. So remember, that was symmetric with respect to the origin and had this pattern that went on 2 lines. So whoops on that, but let's look at it. I'm just going to draw my negative a going here, and then the same distance over here, my positive a. And so this would be the area that we would be finding, this area and that area. And because it's an odd function, do you notice that if you go from negative a to a, that you would have the same amount of area above the curve as you have below the curve? And remember, this is counted as positive and that's counted as negative. So this would end up being what, my friends? Yes, 0. So if you notice you have an odd function, then and you have the symmetry here, that you're going to get 0. You wouldn't even have to do any math on it other than knowing that it's an odd function. And so that would be the good news on that. Okay, so here's some problems out of your book to look at and do. And and remember that tangent is an odd function there. So this is going from negative pi over 4 to pi over 4. So anytime that these bounds are like that, I kind of think to myself, do I have even functions? Do I have odd functions? What do I have? And x to the third is just an odd function. So just this part of it, negative pi over 4 to pi over 4 of x to the third, that part of it right there, without doing any math, that's 0, right? And so, and then what about this other part from negative pi over 4 to pi over 4 of x to the fourth times tangent of, this was dx there, right? And tangent of x dx. And x to the fourth is an even function and tangent is an odd function. And what do you think if you multiply an even function times an odd function? What do you think you get? And if you're going back here and you're thinking about this situation, right, what do you think you get? Well, this, no sign change, right? But here I get that negative of my function. So actually an even times an odd is an odd function. So this actually is an odd function altogether, the whole thing. So I don't have to be able to find the antiderivative of it. I don't even have a method of finding the antiderivative of x to the fourth times tangent of x. And so the good news is that because of this, it is equal to 0. So this is 0 altogether. So we did a lovely, lovely job on it. Okay. So I think I just have some basic comments to make just to kind of wrap up Chapter 4. And I know it's hard to believe that we're done with Chapter 4. It's hard for me to believe that we're done with Chapter 4. And we're going to practice all during spring break. I'm sure that you're going to have a plan since you're going to be locked in your house and not on the beach in Florida during your spring break, of doing some calculus every day. And such good news, right? So this is integrals that we found. We did these in the notes already. And this integral used the basic power rule, the sum difference rule, right, that you find the antiderivative of the pieces, and the constant multiple rule when you held the 3 constant and the 2 constant there. And then this was a basic trig, right? And so you just recognize that, oh, that's a friend, hot diggity dog. And this one is like, well, I can take the integral of x, but I don't know how to take the integral of this crazy square root. You are actually going to learn that in Calc 2. But in Calc 1, they say, yeah, but you know what that looks like. That's a semicircle. And they do that to you a lot with this and also the absolute value. That you can't take the derivative, the antiderivative of it. Can you draw it and find the area? And the answer is yes. So you can do this one. And you can look back on these. And then this one was a trig substitution. And so in order to find this integral, I had to use a basic trig substitution. I had to say that, well, this is half times 1 plus cosine of 2x. And then I could find the antiderivative. And then here, we just did this one today, was a U-Substitution. And then this one was recognizing that it was an odd function and finding it. So those are all the types kind of integrals that we have. And so I hope that you're practicing them. And then I have, of course, some bad jokes. And so there's one of my bad jokes. I'm making a U-Substitution. It's hard to get dumped by a mathematician, right? And so that's terrible, awful. And I love it, though. I think it's funny. And then, and I don't know, the philosophy department is always trying to get involved in calculus. I mean, they just love it. Reggie Williams, he's one of the philosophy instructors at Bakersfield College. He didn't have me for calculus. He actually had me for Math 22. But he did take calculus at Bakersfield College. You can ask him about it. And so I'm sure this is something that he would think is totally cool, right? And so anyway, is that all my jokes? Oh, and here's another funny joke, particularly when you have the proctored exams, right? That moment when the same exercise you studied appears on the exam. So it's when you've done, I'm really, really all about homework, right? Being right on the exam. I do that a lot as a homework problem, right on the exam. It's a reward for having done the homework. And so I'm not going to get too tricky even without proctored, with the unproctored test. Okay, my friends, that's all I have to say. I've said too much, and I'll see you next time.